Hey everyone, my name is Joshua De La Cerda. For those of you who do not know me, this is my presentation, Commercial Pilot Ground, e-presentation, and I'm doing my topic on high performance power plants. Let me switch over to my next slide. So to get started, what is a high performance aircraft? And all the information that I take out of in this presentation is directly from the Jepson textbook. So this right here, 11-2. So the FAA defines a high performance airplane has an engine of more than 200 horsepower. A high performance airplane may be complex or not complex. Likewise, some aircraft may be complex but not high performance. The FAA defines a complex airplane as one with retractable landing gear, flaps, or a variable pitch propeller. So these are some examples right here, like a picture that I provided on the right. And let me switch over to my next slide. Apologies for that. Here we go. So the next thing about high performance systems is fuel injection systems. The low cost and simplicity of carburetors make them a good choice for many aircraft, but fuel injection systems offer significant advantages in efficiency and performance. A lot of old airplanes have carburetors, but a lot of the newer aircraft now that we're seeing are all fuel injected. Less susceptible to icing than carburetors. That's something that's an advantage to fuel injection systems. Fuel injection addresses many of the problems associated with carburetors and provide reduced risk of induction system ice, provide greater efficiency, enhancing engine performance and safely and reducing fuel consumption per unit of horsepower compared to the same engine with the carburetor, which means the aircraft will have improved range, endurance, and economy. And this is very common with high performance aircraft and systems. Let's go to our next slide. Next one. Constant speed propellers. So again, this is something else that's common with high performance aircraft and high performance systems. Constant speed propellers enable you to obtain the best combination of manifold pressure and RPM in different phases of flight to achieve a high rate of climb and cruise airspeed or extend endurance by reducing fuel consumption. A fixed pitch propeller is most efficient at only one particular RPM and airspeed. The main advantage to a constant speed prop is that it converts to a higher percentage of brake horsepower into thrust horsepower over a wide range of RPM and airspeed combinations, therefore allowing the selection of most efficient engine RPM for the given conditions. Here's a diagram I provided on the right, kind of goes through the steps of how constant speed propellers work. This can be found in 11-16. Again, all this information is from the Jepson textbook. Move over to the next slide. Constant speed propeller operations 11-18, meaning how they work. Many types of controllable pitch propeller systems have been developed over the years, including mechanical systems, electric, hydraulic, but the constant speed prop has become the most widely used on modern high performance aircraft today. Although all controllable pitch propeller can improve performance and efficiency by turning more of the engine's power into thrust in different phases of flight, constant speed propellers offer the luxury of automatic propeller control. After you've set the RPM, a device called the governor automatically adjusts the blade angle to maintain that RPM, even if you make a change in the airspeed or flight attitude. For example, if you lower the nose for a descent without changing the engine controls, the increase in airspeed reduction and propeller load causes the governor to increase the blade angle to maintain the selected RPM. And again, another diagram there on the right with the governor, kind of giving you a visual image there. Next, again, turbocharging systems, and this is an 11-11 part of the Jepson textbook. Turbocharging compresses intake air before it enters the combustion chamber, providing a much higher manifold pressure than a non-turbocharged engine. This higher manifold pressure allows you to climb higher and attain higher true airspeeds. You can climb over adverse weather. Turbocharging increases an engine's power by using energy that would otherwise be wasted. A turbocharger uses the flow of the engine's exhaust gases to drive a compressor that increases the density of the intake air. A high-performance airplane's power is typically measured by the amount of air pressure in the intake manifold. This pressure is referred to as a manifold absolute pressure MAP for short. A turbocharger has two main components, the turbine section and the compressor section. Forcing too much gas into cylinders can cause denotation and severe engine damage, which is why a waste gas is installed, which is here on the diagram on the right. Next slide, power controls. Kind of a walkthrough of how these controls would work if a pilot were flying. An airplane with a constant speed propeller has separate controls for engine power and propeller RPM. The throttle controls engine power, which is indicated on the manifold pressure gauge. Propeller RPM can be adjusted using the propeller control and is indicated on the tachometer. When used correctly, these controls can provide the most efficient combinations of power and RPM during takeoff. For example, to develop maximum power during takeoff, move the throttle and propeller control full forward so the engine could produce maximum power and RPM during takeoff. And this can be adjusted throughout different phases of flight. Okay, and last slide here. Something that's also becoming increasingly more common with high performance aircraft is full authority digital engine control, otherwise known as FADIC. And this is in 11-20, the Jepson textbook. The way this works is a computer is associated with systems that manage an aircraft's engine and propeller that are becoming common in high performance aircraft. FADIC, like a digital control module in a car, optimizes engine parameters for best horsepower with minimum fuel consumption. FADIC continuously monitors engine speed, temperature, and pressure through a series of sensors to calculate and deliver the correct amount of fuel for each injector. FADIC systems do not have magnetos or mixture controls and automatically handle engine priming. FADIC aircraft have a single power level for the engine. Just set the lever to desired power and computer adjust engine and power. Okay, and again, everything in my presentation came from the Jepson textbook. This is in chapter 11, and it's called High Performance Systems, and specifically my chapter on high performance power plants. Thank you for watching my presentation, and I hope you guys enjoyed.